Are they all correct? What do you think? They'll work? Okay. Now the work hasn't been shown for all these, but the one and only fact that you need to solve all of these, both A and B and C and D, is what? The knowledge that what? Yeah. Yeah, that pi is equal to 180 degrees. It's not true that pi equals 180. It's right, because that's not true. 3.1415962 is not equal to 100, the number 180. They do not lie at the same place on the number line. But pi, the number pi, is equal to 180 degrees. That's okay. All right. So, and then I might say Maddie's way too, right? Like we can also say, since those are equal, if you do pi over 180 degrees, then that's just 1. Because they're equal, right? Things that are equal when you divide by them. Or, alternatively, 180 over pi. At all times, anything you want, you can multiply in your life. Anything by any one of these three things. They're all 1. So, like, if I take John and I multiply him by pi over 180 degrees, he doesn't change. He's still John. Like, I've done nothing, right? You with me on that? Okay? Same thing. Now, which thing should we multiply when it comes to like converting some of these things? For example, if you're thinking about 108, could you convert 108 degrees to, like, what would happen if you multiplied this by 180 degrees over pi? Like, are you allowed, quote unquote, allowed to do that? Yeah. Like, actually, you are. What are the units that you get? You get degrees squared are the units. Now, that is technically, mathematically correct. Is it like meaningful to us though? The units of degrees squared? No, right? Even though it's like correct, it's not meaningful to us. So like maybe we wanted to get rid of the degree symbol, in which case you just, no harm done, you just need to switch so the degrees cancel out, yeah? This is like the first of many, many unit conversion conversations that we're gonna have over the next 3 days, okay? It's gonna feel like physics or chemistry a little bit. I'm gonna bring units up quite a few times in the next 3 days. I just want you to know that. Fair warning. Okay. That was our first installment. Shh. Guys, Alex has questions. Shh.
Guys, do you know why there's 360 degrees in a circle?
By decree.
Okay.
Someone decided that was a good idea.
Okay.
Yeah. I think it was. I'm gonna hazard a guess. I think it was the Sumerians that did that first, and 360 is a convenient number of things to divide up a circle into, because they thought that there were 360 days in a year, and 360, as you've already encountered as you've worked with degrees. Hey guys. Sorry, I'm sorry. I was talking while you were. That's my fault. Okay. 360 is divisible by like a lot of things, so it's also convenient, isn't it? But in the end, I think actually we're going to try and win you over on radians, and we're going to talk some more about radians today, of course. And if you've already played around with radians in your life, which most of you coming into this class, like I had a warm-up today for you about it, so my expectation is you've thought about radians a little bit. Maybe you're already won over to radians. I don't know. If not, you know, you will be. Maybe even today you will be. Okay. All right, with that in mind, are all these answers clear, right? Without a calculator, we can multiply by whichever thing makes the work happen and call it a day. All right, everyone has a yellow sheet. You see the important. Hey guys, hey guys, I'm still here. All right, hello. Okay, Cam, yeah. The yellow sheet. Yes, this should be my door. The yellow sheet, which is very festive for this time of year, right? Announces the unit 4 is about trigonometry. And actually unit 5 and unit 6 are also about trigonometry. Notice our dates as usual and our plethora of homeworks. Notice also that there's an unannounced quiz after homework 4 at some point.
You just
Okay?
said pop quiz, so we know it's coming.
Well,
We don't know when exactly.
there will be.
Said after
I'll say right now because you're asking. Let me say something about that. You'll have a speed trait quiz after we talk about that a little bit. Even though a lot of you maybe are prepared right now to take one, but we're gonna remind you of a few things over the course of the first 4 days of this unit, and then it's fair game. That being said, I've said, hey guys, can you guys just kill like the side conversation? Okay. Over the course of the next 3 units, we're going to be doing lots of trig. That's all we're doing for the rest of the semester is trig of various kinds. So trig, Unit 4 is trig-based. Unit 5 is also, and Unit 6 are all trig-based of various kinds. Coming at these things from different angles, you might say. Okay, come on. All right. And in each of those units, in this unit and in the next unit, we'll have a pop quiz, and in the Unit 6, we'll have 2 pop quizzes. A total of 4 of these. And I'll drop the lowest one of your scores. They'll always be out of 10 points, 9 questions, 10 points, and I'll say more about that when we actually expect you to be able to do those kinds of problems. But in the next units, any time is fair game, even like the second day of the unit. But this unit, I'm waiting till after homework 4 to answer your question, right? Just because we haven't talked enough about trig yet. So, okay. You have another question?
How is 9 questions but 10 points?
1 for your name. Okay.
Dang.
And also, it just looks better on the paper. You'll see. Okay. All right. So I was down in Virginia, and I wasn't really probably in Maryland because there's a truck in the picture. Okay. We don't have a lot of trucks in this area. Okay. I was down visiting some friends in Virginia, and had to stop for gas, and as I rolled, I almost missed this. I finished fueling up and I was about to take off. And then I noticed the marquee on the sign, and I was like, actually the deepest question I had was why did they put that there? It's a gas station. But I was thinking maybe it was a message of hope to young people around the world about math. Stay in school, it was kind of speaking to us. I took a picture, as usual, and then I put this link near the bottom to to throw you off. Yeah.
Okay. So, when did you go see them?
That was in August, actually.
August of this year?
Yeah.
And how is Diesel 413?
And why is it snowing in August?
Yeah. Hey! And Diesel's 413. Not possible, buddy.
I might not remember all the details.
Hasn't been that high in 5 years. I just kicked your butt.
It's very expensive. It's a remote part of Virginia, though. It was high up in the mountains. Snow-capped mountains in Virginia.
Oh, I've heard of it.
All right, let me refresh your memory. It should be true that if someone at one point told you about radians, then they should have given you the definition of a radian. Because obviously a lot of you are really handy with computations involving radians and degrees. And yet, you may, if someone asked you, you may be like, I don't know what a radian is. So, right? You can do all those calculations on the warm-up and still not know what a radian is and why its definition is so elegant. Are you ready? So there it is in words. As a picture, it's even more beautiful. This is like the multimedia presentation today. Are you ready? Here we go. Wait for it. Wait for it. Wait for it. We're going to wait for it forever. All right, watch. So here's a circle of radius A, and I'm marking off A units along the circumference of the circle. And that angle that's formed is 1 radian. That's how this works. As you guys said, even in the warm-up today, there are pi radians in a straight angle. That is, there are approximately 3.14 of these in a straight angle. Or you could say 2 pi radians in a full circle, 360 degrees if you like. I heard people as they were doing the warm-up discussing both ways of thinking about it. And then here's another beautiful animation that says it all. Here it is. I'm basically doing the same animation again, but I think it's useful to see. There you go. Take the radius, take it out there, bend it. There it is, 1 radian. All right, keep watching. So that's 2 radians. And that's 3 radians. And then just a little more. 3.14 radians. That's 180 degrees. That's a straight angle. Well, there are pi radians up top. And pi radians downstairs as well. 2 pi radians total in the circle, about 6.28 of them, if you were to like keep going around the circle. So you can watch it again, it'll happen again in a second as I was talking about this. So this definition is elegant because it's independent of the size of the circle. You get this same angle whether you're talking about this definition in a circle of radius 1 foot, and you're walking 1 foot along the edge of a circle of radius 1 foot. You get an angle measure marked out 1 radian. Or if it's a circle of radius 1 mile, and you walk 1 mile around the edge of a circle of radius 1 mile, you will have marked out an angle of 1 radian as well. Right? So you see how that's like an elegant definition? And radian, I want you to think of when you hear the word radian, I want you to think of the word radius, right? Like how many radiuses did I mark out? Okay, so is your mind blown? Well, it shouldn't be. I mean, someone should have told you this. Someone should have told you this when they taught you radians. I'm sure they did. You're just being real. Okay. So I just want to have that, lay that meaning on top of you. So already you're seeing that radians are like beautiful. 360 degrees like we already talked about, somewhat arbitrary. But this, beautiful. Okay. The next thing, just mainly because we don't know where else to put it in a course like this, but like we're talking about angle measures today and how to measure an angle, so degrees is a good way, radians is a good way, and then also degrees, minutes, seconds, which is like a way of thinking about degrees in a smaller way. Right? Instead of using decimal points, we might use degrees, minutes, seconds. And really that's like a throwback to bygone days, maybe. I don't know. I mean, how often do we come across the following units in this day and age? Well, I'll tell you one place you might do it. It's like if you're looking up your latitude and longitude on Google Earth or something like that, then it'll give it to you in degrees, minutes, seconds a lot of times or something like that. If you're like a sailor, maybe you think about degrees, minutes, seconds a lot or something. I don't know. Okay. The minutes and seconds have absolutely nothing at all to do with time here. We're not talking about time at all. They've just hijacked the word minutes and seconds to describe another kind of unit, all right? And it makes sense. Like, even if I didn't tell you this, you probably would have guessed, oh yeah, okay, well, degrees maybe is analogous to hours. Therefore, maybe there are 60 minutes in 1 degree. So that's what we call it. We say degrees, because on the surface of the Earth, too, a degree is huge, right? Because we're really far away from the center of the Earth. So 1 degree on the surface of the Earth is maybe not a fine enough distinction, right? Depending on where you are, it might depend, right? So maybe we want to talk about a 60th of a degree. Well, that's called a minute. The 60th of a degree. You could like adjust your heading as you're in the boat by a 60th of a degree, which would be 1 minute off course. Okay. And then even further, split that down 60 seconds in 1 minute. Of course, those conversions are pretty clear if we name them that way. So I guess that's why they named them that way, to remind you of things you already know. Okay, so let's do a sample conversion and feel. I mean, it's just like if someone said 37.425 hours. Convert that to like what you normally think about it as hours, minutes, and seconds. Well, so it's clearly 37. This is clearly 37 whole degrees plus part of 1 degree, right? Just short of half a degree. So I'd like to peel off the degrees, the whole number of degrees, and then I want to think about this degree, this part of 1 degree, and I want to convert that to. Let's start by just converting that to minutes. So what is 0.425 degrees as in terms of minutes? Well, how do you convert just this piece, just this 0.425 degrees? I'm done with the 37. How do we convert just the 0.425 degrees to minutes? Think about the unit conversion conversation we've already had today, Matt. Multiply by 60 over 1, and by 60 over 1 we mean 60 minutes over 1 degree. Yeah, absolutely. So that's 37 degrees. We still have 37 degrees. So how many minutes is that? Someone tell me what you get there. 5.5? 25.5. Okay. 25.5 minutes. All right, and then we can repeat this trick, can't we? By peeling off the 25 whole minutes, and then we have half a minute, don't we? So we could actually do that too. 37 degrees plus 25 whole minutes plus 0.5 minutes. And actually, you maybe don't even have to do the unit conversion on paper. You can just do it in your head. Half of a minute, 30 seconds, right? But let's actually do the conversion here on the end here. 0.5 minutes times 60 seconds in 1 minute gives you what you said, 30. Right? So in the end, we don't usually write the pluses. We just juxtapose them like we have up here. 37 degrees, 25 minutes, 30 seconds. Yes? You like that? A little strange if you're not familiar with it, but I mean, it's not that unfamiliar. You use time all the time, and you're fine with it apparently. So, if that last one needs to be rounded, then it needs to be rounded, right? It just happened to come out really nice on this one because like we made it that way. But yeah, on the last one you could round to an integer exactly, but we didn't have to here because I concocted it for this exact purpose. All right, how about going the other way? I've got something in degrees, minutes, and seconds, and I want to convert it to radians. Okay, well, we'll convert it to degrees first. How about this? I think I can do that, and then we can worry about radians. All right, so how do we convert this to degrees? Well, I know it's 42 whole degrees, and then there are some minutes. How many degrees is 24 minutes? Well, what's the conversion? It's 24 degrees
24 divided
times... Yeah, 1 over 60, and by 1 over 60 we mean 1 degree over 60 minutes. So the minutes cancel out and we have units of degrees still retained. And 36 seconds, we'd love to have that expressed as degrees too. So that's 1 over 60. Yeah, that's 1 minute over 60 seconds. And another 1 over 60 to convert from minutes to degrees. All right, do you agree that the expression, the big, nasty expression that I've written down on the board, and there's no need to like write this out every time you do it necessarily, but I mean, this is what we're going to do right now on your calculator. Do you agree that this huge, nasty expression is actually, in the end, in degrees now? Straight up, every single thing now. This is, of course, in degrees. This will be in degrees once we cancel out the minutes. And this will be in degrees once we cancel out the seconds and the minutes. Boom, boom, right? So, what does that come out to? In degrees, 42.41 degrees, okay? And then it actually asked for radians, didn't it? So convert that to radians by multiplying by pi over 180 degrees, and we'll get 0.740. Okay.
Oh, because we have to do the 3 decimal thing.
I did 3 sig figs just because that's like kind of our practice. If it doesn't say otherwise, we try and yeah. Yeah. It just means three decimal places, regardless of the decimal. Yeah.
It's not like you would just pick a sum of
Is that the answer you're getting to? Can someone just confirm out there?
Yeah.
Good. All right. So, by the way, we should just make sure that that kind of reckons with our understanding of what a radian is. Do you remember what a radian looked like? I mean, think about what a radian looks like. Do you think that 42 degrees, just go gut feeling, do you think 42 degrees is less than or more than a radian? I mean, or is it a lot more? Is it a lot less? I mean, where are we at? And the answer is, does it make sense that it's just a little less than a radian based on our pictures we've been drawing? Okay, good. Just do a little reality check. Okay, good. So it does make sense that in the end, that's our answer.
If you were to get a decimal point, like a large decimal point for like when you multiply the 24, what would the thing come out to be? Would it be like if it was 0.42 something, that's what you got for the 24, and then you added that to the...
Yeah, it might be messy, and then you'd add that to...
Would you just add the
you'd add messy, yeah. You'd add messy plus messy plus messy, and you'd get something wonderful and messy. Okay. All right, next subject that we need to tackle, arc length, okay? And the reason this is the next subject to tackle after having defined a radian, this result is almost immediate once you've defined a radian. In fact, I don't even need to put this formula up here to ask you the following questions. If I am in a circle and I walk and I mark out an angle of 1 radian, and I'm in a circle of radius 1 mile, how far did I go along the outside of the circle? What's the arc length? 1 mile. Okay, what if I did 2 radians? And it's still a circle of 1 radius a mile. then the arc length I've traced out is 2 miles. So what are you doing? And the answer is this. Like, you already know the formula because you're just using it. You're just multiplying the radius by the number of radians to get the arc length. Isn't that wonderful? Now, so this formula is elegant. It's very simple, provided, this is like the big caveat, provided that theta is reported in radians, right? The only reason that discussion we were just having just now was so elegant was because theta was in radians. It was very easy to be like, oh yeah. Now, if it's in degrees, then this formula becomes a lot messier, right? You have to convert to radians. In particular, if theta is equal to, oh, I don't know, a big angle. Look, what if theta is equal to a big angle? Like, how about 2 pi radians? What if our angle was 2 pi radians? Is that an okay angle? That'd be the whole circle, right? What do you get then? You get s equals, what's the formula then if theta is 2 pi? That is the whole circle. You get the arc length is equal to 2 pi r. Right? Is that true? That the arc length of the entire circle is 2 pi r? Yeah, oh yeah, I know that formula. I called it before the circumference formula. But this is like the super circumference formula. You can plug in 2 pi if you want and get the circumference, or anything else, right? Does that make sense? Okay, so do some problems. Here we go. By arc length, and by the way, it's a little unfortunate we're using S. Maybe you don't like that. If you want to use L, not a problem. Some people use L for arc length instead. The other ones make sense. R and theta make sense. Find the arc length, so find S, of a circle with radius 10 inches, that's R, and a central angle, that's theta, of 10 radians. And it's already in radians, so there's no trick question here. I'm trying to, like, on this very first one, no trick question. What is it? What do we get? S equals R theta. So what does that come out to be? Of course, 100 inches. And in case you haven't picked up on this, radians we treat as being unitless, right? We don't, in any of our calculations, we don't write the word radian. Yeah. Yes, it's already in 10. So, and by the way, yeah, we should stop and think. Well, how big is 10 radians? It's bigger than a circle. Is that okay for an angle to be bigger than the circle itself? Yeah, it's almost 2 full circles, isn't it? 6.28 is 6.28 radians is 1 full circle. So this is like not quite 2 full circles. So it makes sense that maybe we get 100 inches. We went like this, right? 100 units we mapped out around the edge of the circle. Great, not a problem. Yeah, so we should stop and say that. Angles can be bigger than 360 degrees, can't they? Okay. Find the radius of a 1-foot arc with central angle 20 degrees. So this time I'm looking for R. Oh, excuse me. Oh, sorry. No, I was right. Of a 1-foot arc. That's S.
Yeah.
With a central angle of 20 degrees. That's omega, but we need it to be. We need it to be in radians, right? I'm sorry, theta. I'm getting ahead of myself to the next slide. Theta. All right, so what does that come out to be? S, 1 foot. By the way, I notice I'm always like carrying the units with me in all these calculations today and tomorrow and the next day because we're gonna, like I said, can have a continuing conversation about units. We just want to be really careful about it. R we don't know, but we will soon. And then 20 degrees, except what's this? Needs to be in radians. So let's convert that to, yeah, it's pi over 9 radians. I can do it maybe right in the middle of my calculation though. There it is, okay? There's an equation, solve for R, the degrees can cancel out. You'll get pi over 9 over here, yeah. Let's actually write that. 1 foot equals R times pi over 9, and again, radians are unitless, and then R equals What do you get for r? 9 over pi, which is a little short of 3, right? Feet. 9 over pi feet. Okay? All right, and then I'd love for you to, some of you are maybe already working on Pac-Man. So keep working on Pac-Man. I'd love to hear maybe different solutions if you have different approaches. Noah, you have a question about?
So it doesn't matter if you change the units of the length of the radius of the answer. So the answer is going to be feet per inch.
Yeah, that's why I said carry the units with you, and you don't even have to have the conversation we're just having. If you carry the units carefully everywhere, it should just come out. But it does make sense that we'd expect the same units for the radius, also from like an intuitional standpoint.
Wait, so how should we write the final answer?
That's a great way. 9 over pi.
No, I'm saying
feet.
for the next one.
Yeah. So
Would it be
it'll be
in
in
the pi?
meters. It'll be in meters.
Yeah, but
Pi's are not units. Pi's a number. All right. How are you doing on this?
I think I already got it.
By the way, if it's hard to see, sorry, the radius of the circle is 10 meters. And that degree in yellow, that angle is measured measures 80 degrees. Okay, in case you can't see it. Give it a
How
try.
many more slides do you have this thing?
3. One of them is not anything you can copy down though. The 2 really. Yeah. Sure, you want to miss this? Okay. I mean, I'm not hurt. Go ahead. All right. Good.
that's not gonna work. Oh yeah, well, because then I subtract that from 360.
Now I feel bad. You need to go. Can someone walk me through it here? What's your, or maybe everyone needs another second. Maybe you're thinking.
Wait, why would I get
Are you volunteering, Rafi? All right, go ahead. Talk to me.
What?
Okay, wait, so 4.5, what did you get? Wait, what is that? 4.5 is, what is that?
4.5. Whatever, it's just.
I know, that's, what does that count though? That's like the,
That's how many times it is.
okay.
So then you multiply 10 times 4.5 and then you subtract 10 and you go circumference.
Yeah, I'm just trying to follow. Maybe it is. So I'm just trying to follow the reasoning on each step. So 4.5 is the number of times.
365.
Yeah, but why are you doing that? What motivates you to do that?
Because I know that the arc length of this times that amount the central angle the arc length of that missing bit times the amount would equal the entire perimeter. And then you subtract another time, you get the central angle.
So I think you're saying 4.5 times, let me actually hear the computation. 4.5 times 4.5 times 10 meters, okay.
And then that would be the entire.
What'd you get?
Right, 2.
Yeah.
Wait, isn't the whole perimeter, isn't the whole circle circumference 2 pi times 10? Isn't the whole circumference 2 pi times 10? 20 pi? Isn't that the whole circumference? I mean, did you just say this is the whole circumference of the circle?
Wait.
The whole circumference of the circle is 20 pi. That's about 60 meters. So that's not the same thing. I don't
So
know.
Chase, are you counting the? Are we counting the two 10-meter parts?
Yeah, of course. The perimeter
Oh,
of the
okay. Well,
region.
then I got it. Okay, so then
All right. I need someone to help again here.
I got you.
Judah wants in. Go.
So it's 10 inches
Okay.
times
10 meters is extra, but whatever. Okay.
times 280 degrees,
Because, so that's the radius
right?
times,
280 degrees pi over 180 degrees.
and then the degree measure of.
Yeah, I know. Yeah.
All right. So Judah, I think I see what Judah's doing.
You have to add plus what
He wants, if we call this S, and he's talking about this arc, not this one. Do you agree this has a degree measure of 280 degrees?
Yeah.
This angle. All right. So do you agree that the arc length S that we've marked, that's not the whole thing. You're right, but that's equal to the calculation he just wrote. S equals R theta.
That just makes it more difficult if you're not using a calculator.
All right. So what does that come out to be? I mean, you can give me an exact answer or a rounded answer.
48.869.
What is it? 14
14 over 9.
14 pi over 9.
or 140 over 9?
14 pi over 9, but once you multiply by 10.
Yeah. So 140 pi over 9. Okay.
Which
Meters.
48.869.
All right. And then we still need to
Add 20.
add 20. Yeah. So our final answer is.
Because that counts the 2 10 meters.
All right. So is that the answer everybody else got out there? Okay.
Yeah.
You're welcome to round that to whatever as well. Thanks for being quiet, everybody. Go ahead, Tammy. Thanks for being quiet. Why do you add 20, Tammy? Why do you add 20? I know. So the question asks for the perimeter of region R, and the perimeter includes not just S that I've marked, but also 2 10-meter segments.
Good job, Cameron.
All right, please stay with me. Shh. We're gonna show you a multimedia extravaganza here. Please stop talking. Thank you. All right, here's the video portion of today's lesson. All right, are you ready? Yeah.
Wait, we're gonna watch Kirk Cousins throw his game-winning pass.
Units are we measuring speed in?
All right, so I'd like to think about which of these is the fastest. We'll just discuss what that means later here.
Oh, that hurts my eyes.
All right.
Appears to be covering the most.
Yeah. So which one looks like the fastest? A looks fastest. I hear you. What about the slowest? Which one's the slowest? Here, I'll play it again. Can I do that?
D. It's gotta be D.
A looks like it's really fast.
Measuring in rate and C and air going the same speed.
Yeah. D.
D looks the slowest.
Yeah.
Okay.
Because C
Are
and
there
B
any
like the same
points that have the same speed?
D is the only
C
one
and B
that
are the
is not
same
following
speed.
the same essentially.
All right.
So you're
I
saying we
mean,
have to take POV to get an A in this class?
all right. Listen. I know the discussions over the next 2 days will feel a little bit like some of the things you've done in POE. But the reason I put fastest in quotes is because we do need some more maybe vocabulary to think about the way in which we mean fast in the pictures we were just looking at. And so we'd like to think about the following two ideas: angular versus linear velocity, okay? This formula that I'm now giving you in yellow should look very familiar. It's the same formula that we were just working with, S equals R theta, except we divided S and theta by some unit of time. On the left, we get then some distance divided by time, and aka that's also known as a velocity, right? A linear velocity. If the radius, if the arc length was 5 feet, well now it's 5 feet per second, right? That makes sense to me. I understand what that means. The one that's a little more unfamiliar to maybe people is this one here. Omega is that Greek letter. And that will be measured in radians, possibly, right? per second now, right? We divided both sides of this equation by some unit of time, and this is the new equation we get that relates a linear velocity to an angular velocity. Linear velocities are like I'm good with, right? I understand linear velocity because like I can run 7 miles per hour, or I can my car goes 60 miles per hour or something like that. I can see that. I understand the speed of light and the speed of sound. It's the amount of distance I cover per unit of time. That makes sense to me. But I'm struggling to come up with an example in the real world of an angular velocity. Can someone help me understand? It's a v. V equals r omega. It's a fancy W. Yeah, don't call it W. It's an omega. It's the last letter of the Greek alphabet. Omega in lowercase. So can someone give an example? Maybe you thought about angular velocity, maybe you haven't, but what's a real world example of an angular velocity? Do you have one? So what angle measure per unit of time are we going to deal with there? I don't know. What do you? I want something that I can like think about how fast something's rotating or something. Yeah. Years? Okay. So what do you mean by that?
I mean, when you're like calculating ratio of years, you look at the angular velocity side of the year, you know, and look at how fast
it's spinning or something? Okay, so it might make like, it might be rotating at 90 degrees per second or something, you might say. That's how
Please find this interruption
no,
for
go
2
away,
afternoon
go
announcements.
away.
First, attention all students. If you choose to dress up for Halloween on this Friday, October 30th, please note that all normal school dress code rules still apply. Students may not wear masks which cover faces while in the building. No face painting is allowed on school property. All face painting must be done off the property. If you have a specific question about your costume, please see your grade level administrator tomorrow, Thursday, before coming on Friday. Also, boys soccer practice is canceled for today. Everyone have a great afternoon, and we will see you tomorrow morning.
All right, listen, please. All right, so let me give you because those aren't still very tangible to me. A good example to me would be like everyone right now is spinning on the Earth, aren't we? Right now, how fast? Really fast. Now I'm not. The way you're going to tell me is not probably linear velocity. You're going to tell me I go 2 pi radians in how much time? In 24 hours. That you didn't tell me just then how much distance I covered. You told me how fast I'm rotating. That is an angular velocity. Or every time you look at your tachometer in your car, do you even know you have one? I don't know. It says 1,000 or 2,000 or 3,000 or 4,000 units or RPM, which stands for revolutions per minute. And by that we mean the number of revolutions of the axle inside the engine block, right? We're talking about like it's turning 3,000 times, 3,000 revolutions in a minute or something, right? That's what that means. It's an angular velocity. We didn't actually tell you how far a point traveled in a given unit of time. All right. I would love to have done these 2 problems, but okay. We are going to flesh out the ideas of angular and linear velocity some more. We want to go much deeper in the next 2 days, but you should be pretty well prepared, I think. Homework number 1.